Hello everyone, and welcome to my presentation. First of all, I would like to thank the organizers for inviting me to give this talk. My name is Klas Modin. I'm from Chalmers University and the University of Gothenburg in Sweden. And the topic of the talk is geometric hydrodynamics and infinite dimensional Newton's equations. So before I begin, let me just say that everything I will be talking about today is joint work with Boris Khesin at the University of Toronto and Gerard Misiolek at the University of Notre Dame. And what I will present is part of a survey that was recently published. I'm not going to present any new results, rather I would like to give you a flavor of the very rich geometry that is involved in this field, which combines infinite dimensional Riemannian and symplectic geometry with hydrodynamics and with connections, as you will see, to many different fields. I think it is fair to say that geometric hydrodynamics started with the work of Vladimir Arnold in 1966. And what Arnold did was he discovered that Euler's equations describing the motion of an envisaged fluid, incompressible fluid in some domain, can actually be stated in terms of Riemannian geometry as a geodesic equation. And how this works, the sort of framework that Arnold gave us, is the following. So you start with some group. So in Arnold's case, it's the group of volume-preserving diffeomorphisms of some underlying manifold M. And of course, this is an infinite dimensional group, and the group structure is you take two diffeomorphisms and you compose them. So so what Arnold did, he was thinking about this as an infinite dimensional manifold, and there are rigorous ways of thinking of diffeomorphism groups as infinite dimensional manifolds. I'm not going to discuss that, but that was sort of the basic idea. And once you do that, you can start thinking about, okay, what is the Lie algebra of that Lie group? And if you think about it, the Lie algebra, so what generates the group of volume-preserving diffeomorphisms, is the divergence-free vector fields. And then the point is that if you take a right-invariant metric on this infinite dimensional Lie group of volume-preserving diffeomorphisms. So if you have such a right-invariant metric, and if that is coming from the standard L2 inner product, then what Arnold realized is that the geodesic equation you get, which will sort of be some equation that traces out some curve in the space of diffeomorphisms, that actually has a direct link to the Euler equations of an incompressible fluid. And the way it works is this. So you have a geodesic equation describing this phi of t. It looks like this, where p is here a pressure field. So if you solve this geodesic equation, and then you take what you have and you construct a vector field from that. So that's taking the phi dot, the time derivative of your curve, and composing that from the right with phi inverse, that gives you a vector field. And this vector field, which is of course going to be time dependent, will then fulfill Euler's equations of motion. So this is the very deep insight of Arnold. And since that work, this field has grown a lot, and today you can treat much more than just the Euler equations within the same framework. So I'm going to talk about some of these developments and just at this point hint to the various fields that this connects to. So you have quantum mechanics, the field of optimal transport, shape analysis, information geometry, of course. We will also touch upon that, and probability theory. These are just some of the fields that connects to this. The extension that we're interested in of Arnold's framework is, first of all, we're not working any longer on the volume-preserving diffeomorphisms. We extend the configuration space to all diffeomorphisms. And then the other thing we drop is we're no longer interested in fully right invariance. So we consider some Riemannian metric, but it doesn't need to be fully right invariant. It's enough that it's invariant with respect to some subgroup, and in this talk, the subgroup is the group of volume-preserving diffeomorphisms. And then in addition to that, we are interested now not in just the geodesic equation, but in Newton's equation. So remember, for Newton's equation, what you need to define it, you need a Riemannian metric, but you also need a potential function. So now we have also a potential function, u, and this potential function is supposed to also have the same symmetry property as expressed here. Okay, so once you have this, you can think about, so what is Newton's equation expressed on the space of diffeomorphism? And this is how it looks like. So it's a second order differential equation, as you can expect. Phi is the map to the diffeomorphism. And then you see here that this map U bar comes from the fact that the U, our potential function, has this large symmetry group, and because of that, it has to have a specific form. And then these are how the equations look like. So you take the gradient of this variational derivative of U bar, that gives you some gradient vector field, and you compose it from the right with your phi. So this will be sort of the force field, and here you have the second derivative. Okay, so let me tell you a little bit more about the geometry behind this. There is a Riemannian submersion lurking here. So first of all, I define this space of smooth probability densities. So it's all the volume forms that integrate to 1. And then I define a map, a projection, that takes me from the group of diffeomorphisms to this space of densities. So the map is defined by just taking the action of the diffeomorphism on the standard Riemannian volume element, which I will denote mu. And what is the point of defining this? Well, the point is that, in fact, Moser showed us in 1965 that this structure is an infinite dimensional principal bundle. It has an infinite dimensional principal bundle structure, which means that the action of the group of diffeomorphisms on dense M is transitive. And this also means that you can identify the quotient, because if you think about it, what is the fiber belonging to the identity here corresponds exactly to the volume preserving diffeomorphism. By definition, it's the diffeomorphism that preserve the mu. So the quotient diff M over the volume preserving diffeomorphism could be identified with the space of densities. Okay, so, and now if we should say something about the metric as well, in this case I take the L2 metric. So this is an L2 metric on diff M, and it's not fully right invariant. It's not invariant with respect to the entire group, but it is invariant with respect to the group of volume preserving diffeomorphisms. So that means that it actually induces also a metric on the space of densities. And this metric is often called the Otto metric, or the Wasserstein-Otto metric, an H-1 Sobolev metric on the space of densities. And the nice thing with this metric is that it induces the L2 Wasserstein distance. So that's already there, a nice connection to other fields. I also said that the fact that you have a potential function that is invariant combined with Moser's result implies that this potential function must correspond to some functional on the space of densities. So that's where this comes from. So now when you've seen a little bit more about the geometry lurking behind this whole thing, let me give you various other forms of Newton's equations. The first form, the one you see here, is the one I already showed you. But because of all these symmetry relations, you can also apply this very rich framework of symplectic reduction. So if we do that in the first step, we do what is called a Poisson reduction, then we end up with a system that is now a Hamiltonian system, evolving on some space, and this space is going to be given by the dual of the space of vector fields times the densities. And you should really think of this space as taking the full cotangent bundle of the space of diffeomorphism and then quotient by the space of volume preserving diffeomorphism. Then you end up with this space here. And the equations of motion have a very nice form. You take some m corresponding to the element in the dual of vector fields, and then it's related to the vector field via some Hamiltonian function. And the m is transported by this vector field, but then you also have a term here coming from the potential function. It should be equal 0 here as well. So that's the first part of the equation. And then the second part is that the density itself is just transported by the vector field v. And then because of this very special structure, because you have there's a Riemannian submersion, you can also look at just horizontal solutions. So that's when you start your initial velocity field to be orthogonal to the fibers. And if you do that, because this is a Riemannian submersion, they will remain orthogonal. And if you do that, you end up with a system on the cotangent bundle of the space of densities. The other way of looking at this, if you don't like to think about Riemannian submersions, is that what we're doing is we're taking a Poisson system and we're restricting that Poisson system to just one of the symplectic leaves. And that symplectic leaf turns out to be exactly the cotangent bundle of the densities. And then you have some fiber variable, theta, which evolves in the dual of the tangent space. And the equation for that looks like this. It's some sort of Hamilton-Jacobi type equation, which also involves the potential. Plus, we have still this transport part. So these are three forms of these equations. And my point is that by sort of specifying various potential functions and various metrics and using some transformations, you can see that a lot of equations have this form. So here I listed some of them. The first bunch here are the ones based on the Wasserstein-Otto metrics, the one I just showed you. But you can change the Riemannian metric on the space of diffeomorphism. You can, for example, relate it to the Fischer-Rao metric instead, and then you get another bunch of equations. And then you can also do something called the Madelung transform once you have a system on the space on the cotangent bundle of densities. And that gives you another set of equations. There are lots of connections here to various equations, and I won't have time, of course, to discuss all of them. So I'm going to give you just one sort of case study. So here we start with the middle form of the equation, only now we do it in Lagrangian form. So we have a vector field and a density, and we have a Lagrangian function, which is something like this. This is, if you like, corresponds to the Riemannian part of the Lagrangian. And if you just look at this system and you write down what you get Berger's equation. This is sort of expected. And we know also that Berger's equation is sort of governing the dynamics behind optimal mass transport. So the geometric way of saying this is that horizontal solutions to the boundary value problem corresponds to optimal mass transport with respect to the L2 cost function. But let's now change the Lagrangian a little bit. So we take as potential function the Fischer function, and we multiply it with some h bar squared. And the cool thing is that if you do this, then horizontal solutions actually give you the Schrödinger equation. The only thing you have to add to the form to make this work is the so-called Madelung transform, a transform that goes from the cotangent bundle of densities into wave functions, psi. Okay, and this result is very standard. It was known already from the start of, the dawn of quantum mechanics. It was derived by Madelung, so this is known. And then it was picked up later, I think, in a stochastic framework by Nelson and others. So this is already quite nice. But then you can change this a little bit further. by saying, okay, I take my Planck's constant to be imaginary. So what that means is that you get some I square equal -1 term. So you shift the sign here. You get a plus sign here instead. And then if you do it like this, and you apply the Madelung transform again, you no longer get the Schrödinger equation, but you get something like two decoupled heat equations. One which is one which is the heat equation, and one which is the backward heat equation. So you see there's a minus sign here. So of course this is a bit worrisome, because this means as an initial value problem, this is not very well posed, because you have a backward heat flow here. However, you can still look at the two-point boundary value problem. So that's the problem corresponding to optimal transport, if you remember. And if you do that, then you sort of reverse time for this equation, for the second heat flow here, so that it becomes a standard heat flow, but backward in time. And then the relation to your original density, rho, is that you need to multiply this psi plus and psi minus. The psi's here are no longer complex, they're just real valued. This problem is known as the Schrödinger bridge, sort of studied already by Schrödinger in a probabilistic setting. And then it was picked up later by several authors, in particular Sambrini in the 1980s, and more recently it's been used also in the optimal mass transport communities, and where it's referred to as entropic regularization. One reason that this is very nice is that it gives you a fast way of computing, because if you sort of think of this as just a slightly modified cost function for mass transport, then you see that the problem you need to solve to solve the transport problem becomes a coupled problem like this, where you sort of need to solve for the psi plus and the psi minus at each end of the time span, so at t equals 0 and t equals 1, right? And the relation between them is you have to apply the heat flow. So that's what I mean with this exponential of the Laplacian here. And then you get these equations, and if you just iterate that, you get a numerical method for solving this optimal transport problem, which is called the Sinkhorn method. Okay, so I don't think I have much more time today, but I just wanted to show you some examples where this where you see some connections between hydrodynamics and other fields by sort of looking deeply at the underlying geometry. Okay, thank you very much, and if you have any questions, I will now be available to answer them. Okay, thanks.
Thank you very much. There are no questions in the chat, I believe, but perhaps in the room.
There is some question in the room. Yeah, I have one person, Gert. Come here, because we cannot understand in Zoom. Just here and speak to the...
Speak here?
Yeah, you have to answer that.
Okay, just a little question. I was wondering if you can comment and explain why your two horizontal solutions are multiplying in your equation. Last slide.
Sorry, again, can you... What did you say?
In your last slide, the two horizontal solutions were multiplied and as if they were independent. So basically, can you explain why and comment about this?
Oh, you mean the relation between this psi plus, psi minus, and the rho?
Yeah, exactly.
Exactly. Okay, so this comes. So I was talking about this Madelung transform, right? So normally, when you talk about Madelung, you do it in actually, that's exactly what we saw in the previous talk. That was exactly the Madelung transform, but applied to a finite dimensional system. When he was going from the cotangent bundle to the wave functions, he was applying the standard Madelung transform. So I'm doing this now, but the Planck's constant I have is sort of imaginary. So you get, instead of getting one complex wave function, you get two real valued positive functions, right? They are not probability densities. They are somehow like half densities, or not exactly, but they have exactly the property that when you multiply them, you get back. And when you take the psi plus and the psi minus and you multiply them, you get the probability density back. So the fact that you have to multiply them to sort of get the density, that is built into this real version of the Madelung transform, which actually can be seen. I didn't say that, but this real version of the Madelung transform is if you like, two copies of what is also called the Hopf-Cole transform, which is a way to relate the viscid Burgers equation to the heat flow. Does that answer your question? I'm not sure.
Yes.
Yeah.
There is another question. Can you come in here? And that will be the last question. Sorry.
Thank you very much for a wonderful talk. So in your Lagrangian, in order to get quantum mechanics, you have to add this extra term, which is the square of the gradient divided by the density. So this, it seems to be constructed in order to get quantum mechanics. But is there a natural reason why that has to appear in some sense? A geometric reason why that would be natural to be there?
I mean, okay, that's a good question. So in the example I showed you, I remember I was not doing it the standard way. I changed the sign. So then it's called entropic regularization. And it's a very good question. I mean, because the way that we sort of like to think about this is that term corresponds to the potential energy in your system. You know, and just as we saw in the previous talk, what we're doing is, one way of looking at that is that we're doing dynamics, Hamiltonian dynamics, on the space of probability densities, right? So this is some sort of Hamiltonian, or this is some potential function on the space of probability densities. And I mean, so in what sense is it natural? Well, it's related to Fischer, to the to entropy. Sorry, to entropy, of course. And the relation is there are several ways to see the relation, probably you know, but one relation is to say that the Fischer functional is sort of the rate of change of entropy along a heat flow. So perhaps that gives you some sort of motivation for why to introduce it, but I don't have a good answer of if I don't see a canonical way that it has to appear, but maybe there is, but I can't give you that. No.
Thank you very much.
Thank you. Jeff,
Thank you.
Thank
you. Let's thank the speaker once more. And thank you very much. Thank you very much, everyone, for attending the session. Thank you to the speakers and to the organizers for leading this rather hybrid way of chairing a session in very good to a very good results. Thank you very much. This is the end of our session.